Good morning, everyone. Welcome to the class of CE331 Environmental Engineering 1. So, we're discussing about the water quality parameters. Now, we'll start with the alkalinity today. What is alkalinity? First of all, tell me what is acidity? What is acidity? The presence of H plus hydrogen ion, right? Right? Can you hear me, guys?
Yes, sir.
जी सर।
Yes, sir.
Yes, sir.
Yes, sir.
So, what is acidity?
স্যার যে
I just
দ্রবণে এইচ প্লাস আয়নের মান বেশি হবে সেটা বেশি অ্যাসিডিটি হবে।
so acidity is basically right. So, acidity is basically the measure of hydrogen ion concentration, right? What is alkalinity? Alkalinity is exactly the opposite of acidity. Opposite of acid. So this is opposite. That means alkalinity is the acid neutralization capacity. Acid neutralization capacity. For example, this is solution X, solution Y. So alkalinity of solution X, if the alkalinity of solution X is greater than the alkalinity of solution Y, that means X has greater power to neutralize acid. That means if you put same amount of acid here and here, acid, okay, this will have greater power to neutralize. Neutralize means to deactivate, okay, acid. That means to absorb hydrogen ion, to absorb, neutralize hydrogen. Which one has the greater capacity? X. Because alkalinity of X is greater than alkalinity of Y. Okay, is it clear, guys?
Yes, sir.
Now, chemically, who causes the alkalinity in water? What are the agents? The agents are bicarbonate ion, carbonate ion, and hydroxyl ion. Bicarbonate ion, carbonate ion, and hydroxyl ion. What happens if you have bicarbonate ion, HCO3? When you have bicarbonate ion, this has the capacity to neutralize acid. How? It can take hydrogen ion, absorb it, and produce H2CO3. That means this is neutralizing. This is neutralizing the acid. Okay. Again, carbonate ion. This can again take hydrogen ion. Okay, absorb it or neutralize it and produce HCO3 plus minus 2 plus 1 minus 1 minus 2 plus 1 minus 1. Okay. Again, hydroxyl ion can take or absorb or neutralize hydrogen ion to make it H2O. So basically, these are the agents which has the power to neutralize the acid, the acid, the acid. So that's why they are called, they actually cause the alkalinity in water. They cause alkalinity. So alkalinity is basically summation of bicarbonate ion plus carbonate ion plus C2 plus hydroxyl ion. Alkalinity, so this is plus plus plus. Now what is opposite to alkalinity? What is opposite to alkalinity? As I told you, acidity, am I right? What is
Yes, sir.
opposite to alkalinity? Acidity. So this is negative acidity. So summation of this is actually alkalinity water. This is actually a natural. This is actually what that naturally exists in water. Alkalinity is expressed in terms of equivalent calcium carbonate. You can always express them. Unit is in milligram per liter. This alkalinity unit is in milligram per liter as calcium carbonate. That means you convert the weight of bicarbonate as calcium carbonate, equivalent to calcium carbonate. Then you convert the weight of carbonate ion equivalent to calcium carbonate. Hydroxyl similar and hydrogen similar. Okay. Now the thing is, as I told you here, that bicarbonic acid H2CO3, it dissociates to give you hydrogen ion and bicarbonate ion. Okay. Now this bicarbonate ion can also dissociate to give you hydrogen ion and carbonate ion. Remember, this is bicarbonic acid. This gives you hydrogen ion and bicarbonate ion. And this bicarbonate ion itself is gives hydrogen ion and carbonate ion. I showed the direction of the equation of chemical reaction in this direction. Sometimes this direction can also happen. This direction can also happen. That means carbonate ion can take one hydrogen ion to form this, and again these can take one hydrogen ion to form this. Now the question is, when would this happen and when would this happen? This actually solely depends on the pH of water. So depending on the pH of the water, different types of reactions may occur. For example, if you look at this table, pH scale 4.5, 6.3, 8.3, 10.3. So pH is increasing in this direction. Alkalinity classification, type of alkalinity. When your pH is less than 4.5, that means here less than 4.5, starting from 0 to 4.5, there is actually no alkalinity. These are all acidity. Of course, pH is lower. That means what? pH is lower, that means what? Acid, right? Acid means pH
Yes,
is
sir.
low. So this is so low, the pH is so low, that means acidity is so high that there is no alkalinity, all acidity. Okay? That means this carbonic acid actually does not dissociate. What is dissociation? And that means this H2CO3 becomes H plus and bicarbonate ion. This does not happen. This does not happen when your pH is less than 4.5. Now, when your pH is increasing beyond 4.5 to 8.3 in this range, then what happens? Then the bicarbonic acid, which was previously undissociated below 4.5 pH level, will now dissociate and give you hydrogen ion and bicarbonate ion. Hydrogen ion and bicarbonate ion. Hydrogen ion and bicarbonate, HCO3 minus. Okay. What are the species we get from here? Major species. This is the chemical reaction. This is the chemical reaction we are observing from 4.5 to 8.3 in this range. From 4.5 to 8.3, this range. What are the major species in this range? What are the major species in this range? It's quite understandable that you will get this and you will get this. Alkalinity species. So bicarbonic acid will have this and bicarbonate ion this. Previously, when it just starts dissociate, when it just starts dissociate bicarbonic acid to bicarbonate ion near 4.5 pH, then H2CO3 is much higher concentration, each at much higher concentration than this one. But as the pH increases from left to right, more and more bicarbonate acid dissociates to give you bicarbonate ion. That means the concentration of this is decreasing and the concentration of this is increasing. Am I right?
Yes, sir.
Okay. Now at a point at 6.3, H2CO3 concentration is equals to bicarbonate ion concentration when at H6.3. Now, if you go beyond 6.3, then this concentration gets higher than this concentration. Okay, and when you reach 8.3, then almost all of them are bicarbonate ion. There is no carbonic acid anymore. Okay, now what happens at 8.3? So at 8.3, one thing we realized that we have mainly bicarbonate ion. Okay, now as you go beyond 8.3 to 10.3 or higher, this bicarbonate ion, now this bicarbonate ion dissociates to give you carbonate ion and hydrogen ion. This gives you to dissociate hydrogen ion and carbonate ion. Hydrogen ion and carbonate ion. Initially, this is much higher concentration than this one. But at 10, as you go further rightward with increasing pH, the concentration of carbonate ion increase and the concentration of bicarbonate ion decrease. Why? Because bicarbonate ion is dissociating to give you carbonate ion. So this will increase and this will decrease. Alright.
Yes, sir.
Yes, sir.
Now in this way, when you reach 10.3, then your bicarbonate ion concentration is equals to carbonate ion. If you go beyond 10.3, then this concentration will increase. I mean, the relative concentration of carbonate ion will be higher than the concentration of relative concentration of carbonate ion will be higher than the bicarbonate ion.
Bicarbonate.
So in this range from 8.3 to 10.3, you mainly get bicarbonate ion and carbonate ion. These are the species, major species that you will get. Major species. Minor species, there might be a little bit of them. We are not concerned about it. We are concerned about the major species. There's those species which are uh, at, at, at the highest concentration. Okay. If you go 10.3, beyond 10.3, then you will have carbonate ion and you will have hydroxyl ion, hydroxide or hydroxyl ion. That means when your pH is greater than 10.3, then H2O now dissociates to give you and breaks down to hydrogen ion and hydroxyl ion. So you will get hydroxyl ion here, right?
Yes, sir.
So this is actually easy. 4.5 and 8.3. 4.5 and 8.3. Remember this. Beyond 4.5, undissociated H2CH3, no alkalinity, no alkalinity, because this cannot dissociate. Okay, above 4.5, this starts dissociating and gives bicarbonate ion and hydrogen ion. At 8.3, now this starts dissociating to give carbonate ion and hydrogen ion. So 4.5 and 8.3. Now at 6.3 they are equal, and at 10.3 they are equal. That's it. So summary is pH. So summary is pH 4.3 or 4.5, 4.5 and 8.3. So 4.5 and 8.3 undissociated, no alkalinity. From this to this in this range, H2 CO3 dissociates to give you hydrogen ion and carbonate ion. And beyond 8.3, I'm sorry, now beyond 8.3, this one now dissociates, starts dissociating to give you hydrogen ion and carbonate ion. Okay, now at 6.3, they are equal, and at 10.3, right, they are equal. So at 6.3 they are equal, and at 10.3 they are equal. And you can easily know, determine that in this range, who are the species? What are the species guys in this range? What will be the species present in this range? Look at this equation, this and this, right? Did you get this here, carbonate ion? Hmm?
No, sir. Bicarbonate acido.
Yeah. And who is present in this range? In this range, after 10.3, you have this and this. Beyond 10.3, here, H2O dissociates. So you will get carbonate ion and hydroxy ion. CH2 minus 2 and beyond that. That's it. Okay? It's very important to know. Oh, so the thing is here now, look at this table now. Look at this table now. We see that from 4.5 to 8.3, you have some alkaline species. What are those alkaline species? H2CO, H2, bicarbonate ion, basically, right? Bicarbonate ion. This one, alkaline species, is bicarbonate ion. And 8.3, it gets changed and something else. Now, the thing is, when in the laboratory, we, how would you determine these things? We use an indicator. What is indicator? Remember, indicator. Indicator is what? Nirdeshak, right?
Yes, sir.
Which changes the color to tell you the end point of a titration. Indicator changes its color, right? It changes its color to show the end point of the reaction. Now, methyl orange alkalinity that changes the color in this range to this range, and phenolphthalein alkalinity, phenolphthalein, phenolphthalein alkalinity, P alkalinity that changes the color at this range 8.3. So the alkalinity from pH 8.3 and beyond, we call it P alkaline. The alkalinity pH 1 to 2 important, right? So pH 8.3. This portion alkalinity we call it what? Phenolphthalein, P alkalinity, because phenolphthalein indicator changes the color at this point. This is P alkalinity. Now look at here that at point 10.3 you start getting hydroxyl ion, and this is called caustic. So beyond 10.3, the alkalinity beyond 10.3, we call it caustic alkalinity. Okay? Caustic alkalinity. Fine. So now The alkalinity from 4.5 to 8.3, from 4.5 to 8.3, this alkalinity we call it what? M alkalinity, because the methyl orange indicator changes the color at this point. And from 1 to 4.5, tell me what is this? Do you have any alkalinity at
So no
all at this point?
alkalinity.
No alkalinity. So this is no alkalinity. System 5. Okay, there is no alkalinity. From 1 to 4.5, no alkalinity. Is it clear, guys?
Yes, sir.
Acidity. Same thing, the opposite. That acidity is measured in terms of calcium carbonate. Okay, so this is measured in terms of calcium carbonate. Calcium carbonate is actually a base because it gives you, okay, needed to neutralize H2CO3. So base and acid. So pH is a measure of the concentration of the free hydrogen ion. Acidity is a measure of free hydrogen ion. Now total acidity would be what? Total acidity would be H2CO3. Why H2CO3? Because H2CO3 gives you H2CO3 gives you what? Hydrogen ion. Let's write it here. Because H2CO3 gives you what? Hydrogen ion. Alright?
Yes, sir.
So H2CO3. Hydrogen ion, of course, this is acidity. Hydrogen ion, of course, will come there. And bicarbonate ion also gives you acidity. But this one actually dissociates to give you hydrogen ion and carbonate ion. Right? Right? And
Yes, sir.
acidity is what? Acidity is the opposite of alkalinity. And alkalinity comes from hydroxide ion, so this is negative. Okay, and summation of all are total acid. Acidity classification. Similar to the classification of alkalinity, we have acidity classification. Same thing. 4.5 undissociated H2CO3. Okay, and then H2CO3 dissociates this. Again 8.3 H2CO3 dissociates and gives this. Okay, similar to this. Okay. And above 10.3 H2O starts dissociating to give you hydrogen and hydrogen ion. Now here the acidity from 0 to 8.3, that from 0 to 8.3, that acidity is called carbon dioxide acidity, natural acidity. Okay, and the acidity less than, I mean, smaller than 4.5 pH, starting from 0 to 4.5, this is called the mineral acidity. It's called mineral acidity. And beyond 10.3, there is no acidity. If you go there, beyond 10.3, there is no acid. No acid. So, no acid. Okay, and then from 8.3 to 0, that's called natural acid. That is natural acid. And from 0 to 4.5, that's called mineral acid. Mineral acid. While we got no alkalinity from 1 to 4.5 or 0 to 1.4.5, we got no acidity from 10.3 to 40. Of course, because pH is when pH is smaller, the acidity is higher. pH is higher, acidity is smaller. When pH is smaller, alkalinity is lower. No alkaline, right? Is it clear, guys?
Yes, sir.
Yes, sir.
Okay. This table is a summary from the previous two classes we saw so far. Variation of carbonic acid species with pH values. So whenever your pH value is less than 4.5, that means you have no alkalinity. So undissociated carbonic acid, no alkalinity, mineral acidity, no alkalinity, mineral acidity. When it's from 4.5 to 8.3, that is M alkalinity starts. M alkalinity starts from 4.5 to 8.3. From 4.5 to 8.3, M alkalinity starts. No mineral acidity, M alkalinity, and whenever it is 6.3, then H2CH3 equal to bicarbonate ion, and when it is around 8.3, then this one it has much higher concentration than this one. This one is much higher concentration than this one. Similarly, whenever it's beyond 8.3, then these starts dissociating. So dissociation of bicarbonate ion. What is bicarbonate ion? This is bicarbonate ion. Starts. And P alkalinity starts. So from 8.3 to 10 above, P alkalinity starts exist actually. And at 10.3, you have bicarbonate ion equal to carbonate ion. And at greater than 10.5, this concentration is much higher than this concentration. Is it clear, girls?
Yes, sir.
Yes, sir.
I mean, this is at 10.3 they are equal, but at 10.5 or something like that, this is much higher than this. Okay. Let's talk about the next topic, hardness. What is hardness? What is hardness? Why do you call a water hard? Any idea? Where does this term come from? hard water, hardness. We call it hard water. Hardness comes from hard. Hard means what? Difficult, right? Hmm?
Yes, sir.
Sir.
Yes, sir.
Hardness. Hard water. The reason is because these types of water are difficult to wash with. These are difficult to wash with. For example, if you use this water to wash your clothes, it is difficult to wash them. That means this water is not suitable to wash with soap and detergent. That's why this is hard water. Simple. Why hard water? Because this is difficult to wash with soap and detergent. These things. Clear?
Yes, sir.
Now the question is why this happens. Why is this is hard water? The answer is when you have divalent cations in your water. For example, what are the divalent? That means valence is 2. What are they? Iron plus 2, calcium plus 2, okay? Manganese plus 2, magnesium plus 2. Divalent cations, if they are present in water, then do you know what happens? They actually react. They react with soap. They react with soap. They react with soap, and that makes them difficult to wash with. Because if soap is reacting with them, that means soap is not performing its actual function, which is to wash the cloth by removing the grease or oil. Okay, so since these species, if present in water, react with soap, that's why they reduce the efficiency of the soap. That's why the water is hard. Is it clear, guys?
Yes, sir.
Yes, sir.
How do you measure hardness? So hardness, we measure it by summing all the divalent cation concentration like calcium ion, magnesium ion, iron, manganese. Okay. Now, what are these things? These, these, these. Hardness. And you know what? Can you add an apple with a mango? Apple and mango. Can you add them? That's different things, right? Let's take another example. Can you add kg with gram?
No, no, sir.
No, sir.
1 kg plus zero point 0.5 gram. Can you do it? No. Either you have to change it to gram, or you have to change gram to kg. Alright? So you can write, okay, 1000 gram plus 0.5 gram. Now they're equal unit, same unit. So you can add 1000.5 gram. Is it clear?
Yes, sir.
Yes, sir.
Similarly, you cannot add these directly because the atomic weight of these is different than the atomic weight of this. Atomic weight of calcium is around 40. Atomic weight of iron is around 56 to 57 approximately. Am I right? Hmm?
Yes, sir.
So there cannot be. So what we can do before summing them up, to calculate the hardness, we convert them into a same equivalent unit like this. Same equivalent unit, gram. What do you do for that purpose is we express all of them in terms of calcium carbonate. All of them in terms of calcium carbonate. That means you all convert them, for example, in terms of gram. Okay, and then we add them. What do we do? Well, what is the molecular weight of calcium carbonate? Tell me. Calcium is 40, am I right?
Mm, yes,
Plus
sir.
carbon is what? 12. Oxygen is what? Huh? Huh? What's the atomic number of oxygen?
18, sir.
8.
So
18.
8, sir.
8. So molecular weight is usually multiplied by 2. So 60.
16, sir.
Yeah. What is the atomic number of carbon? 6. 6 into 2 is 12.
12, sir.
What is the molecular atomic number of calcium? That's 20. I mean, right? So 20 into 2 is 40. Now 16 into how many oxygen? 3. So tell me what's the value? What's the value? Calculate it. Huh?
100.
And now what is equivalent weight? There's a molecular weight. What is the equivalent weight? Equivalent weight is actually molecular weight divided by valence. So what is the valency of calcium carbonate? It dissociates, then it gives you calcium ion and carbonate ion. How much hydrogen it can take? 2, right? So valency
2.
is equals to 2. And what is the molecular weight? 100. So it becomes what? 50. Equivalent weight of calcium carbonate is 50. Similarly, what is the equivalent weight of iron? What is the equivalent weight of iron? Iron, the molecular weight, equivalent weight of iron equals to what is the molecular weight, guys? I say 56 or 57, am I right? 56 or 57, right? Uh, Something like that. 56 or 57. Yeah, right. Around 56 point something. For example, take 57, approximately, okay, approximately. Divided by what is the balance in here? Plus 2, am I right? So plus 2. Tell me what is the value here. 27 point or 28 point something.
28.5.
28.5, right? So whenever you add this hardness for iron, what you do, hardness equals to summation of iron plus calcium plus da, da, da. So iron, you are representing iron as equivalent what? Calcium carbonate. Therefore, the calcium carbonate equivalent weight will go in the numerator, and the iron unit equivalent weight will go at the denominator. So 28.5 or something, 27, I forgot. So 28.5. So this is 50 here by 27 points. So this may be uh, 56 point something. Let's tell 56. Okay, so that becomes uh, 7, right? Yeah. So that makes it 27.5, something like this. So 27.5. So 50 divided by 27.5. Is it clear? Equivalent weight of calcium carbonate, equivalent weight of iron. Is it clear? Oh, not iron. Here, this is iron. 50 is the calcium carbonate and this is the iron. Is it clear, guys?
Yes, sir.
And again for magnesium, uh, equivalent weight is 12.15, 24 divided by 2. For calcium, equivalent weight is 40 divided by 2. And for manganese, this is 57 divided by 2, 27 point something. Is it clear? So you add them up and you get the total hardness, which is equivalent weight of calcium carbonate, expressed in terms of equivalent calcium carbonate. As I told you, divalent cations cause hardness, a quality that manifests itself in neutralization of soap. These divalent cations react and neutralize the soap. Okay. Fine. Cation, anion, type of hardness. What are the cations? Hardness, calcium, magnesium, iron, manganese, strontium. These are the divalent cations that can cause hardness in water. Okay. Okay. Now, what about alkalinity? Who causes alkalinity? Bicarbonate ion. There will be a negative sign. Okay. Hydroxyl ion, negative, -2. So these are the species that cause alkalinity in water, right? So these are hardness causing species. These are hardness causing species. These are alkalinity causing species. These are alkalinity causing species. Does they cause hardness? Do they cause
No, sir.
hardness? Because they are +1, +1, +3. Okay. So they don't cause. So this is non-hardness. Do they cause alkalinity? Sulfate, phosphate. Do they cause
No,
alkalinity?
sir.
No.
No,
So
sir.
this is non-alkalinity. Okay. So if you get the hardness from the connected with the alkaline species like calcium bicarbonate, calcium get reaction with bicarbonate ion and you get calcium bicarbonate. So we call it alkaline hardness. We call it alkaline hardness. Now, if this happens, for example, hardness species connects with non-alkaline species. Then non-alkaline hardness. Non-alkaline hardness. Why non-alkaline? Because there is nothing called, there is no species that causes what? Alkalinity. Is there any species that causes alkalinity? Tell me. Is there any carbonate,
No, sir. No, sir.
bicarbonate, carbonate? No. So this is non-alkaline. Is there any species that causes hardness? Yes, calcium. So non-alkaline hardness. This is alkaline hardness. Sometimes if this associates with this, like sodium sulfate, like this, then this is non-hardness, non-alkaline. Non-hardness, non-alkaline. Clear?
Yes, sir.
Okay. Arsenic is very important for us to know in Bangladesh actually, because you'll see that majority, a massive area of Bangladesh, especially in the southern part, groundwater is affected by arsenic in groundwater, by arsenic concentration. And this is serious pollution because this arsenic can cause cancer and other life-threatening diseases. Okay, let's look at this map. By the way, WHO guideline for maximum desirable arsenic concentration in drinking water is 0.01 milligram per liter. In Bangladesh, maximum acceptable concentration we have used 0.05 milligram per liter. Since we already have severe pollution prevalent in our country, therefore, if we are so strict with this value, then there will be a lot of location that will not get the pure the drinking water to drink. So for Bangladesh, this is 0.05 milligram per liter. What does that mean? That means if your drinking water has arsenic concentration greater than 0.05 milligram per liter, that means this water is what? Dangerous, unsuitable. Dangerous, unsuitable to drink. Is it clear?
Yes, sir. Sir, is it
Yes,
zero
sir.
point 0.5 or 0.05? স্যার আপনি
According
যেখানে
to WHO guideline, this is point. This is, oh sorry, this is 0.05. I'm sorry, it's a typo. Whatever it is, let's cut it down. This is 0.05 milligram per liter. So now look at this graph figure. It shows the regional trends in groundwater arsenic concentration in shallow ways. That means groundwater table is not much deeper, it's shallow. This is ground, this is shallow, and this is deep. This is shallow and this is deep. Okay, now look at this figure. Red, what is, oh, by the way, arsenic concentration 0.05 milligram per liter, am I right? If you change it to microgram per liter, then it is what? You have to multiply it with 1000, am I right?
Yes,
So
yes.
5 microgram per. Milli is 10 to the minus 3, so micro is 10 to the minus 6. So you multiply it with 5. So 5 microgram per liter. These are in microgram per liter. 5 microgram per liter. So if you look at here, did you see that arsenic concentration is, am I right? 1, 2, 3. Oh, sorry, this is 50. Yeah, 1000, 1, 2, 3. Why didn't you tell me? 1, 2, 3, 50 microgram. So this color, starting from this color, this is dangerous. And look at there. These are all suitable or unsuitable?
Unsuitable.
Huh?
Unsuitable.
Unsuitable. Severe pollution, arsenic. Do you see? This cannot be drunk. This, not this portion. This. So this groundwater is dangerous to drink. Severe pollution. Do you see? Almost 50% of the area. Uh, myriad of tube wells have been colored red in this location because they found arsenic concentration above the standard limit. Okay, most of the arsenic found in water derives from industrial discharge, but in this groundwater, these are basically naturally occurring. Okay, acute poisoning by arsenic involves central nervous system. It can damage your central nervous system, leading to coma and for doses 70 to 180 milligram to death. WHO guideline value is 0.01 and Bangladesh standard is 0.05. Okay. Arsenic toxicity leading to cancer occurs due to excessive intake over a longer period of time. Presence of arsenic in Bangladesh was first detected in 1993 at Japanese movement. 1 in every 3 shallow tube wells out of 3, 1 above acceptable limit. That means 33%. 1 by 3 is what? Around 33.3, right? Then 3% tube well showed contamination above the acceptable limit. I think they were not suitable to drink. Next day we'll start from here. Any questions, guys? Any
No, sir.
questions?
No, sir.
No, sir.
Okay, then thank you very much for attending the class. Have a good one.
Sir,